Okay, so we were just talking about the finite state machines where we saw that okay, there is a combinational circuit which you can have series of inputs coming from your, let's say if there is a flip-flop circuit, right, or flip-flops, and this is giving you the input which gives you the previous state. There are different inputs which could come, and the output of this uh, is decided by not just this state, but so that means previous states and the inputs, right? So something like that. So this is output, and this is again combinational circuit. So that means you are changing the state of how you are playing with it is you are retaining the states in the storage elements. That is the key, right? Other than the combinational circuits, right? And that is what is made of also with gates, right? That is the beauty about this FFs. So now the question is very simply, can you tell me what you mean by that? This, how do you make a state diagram, right? State diagram means you are saying okay, I have initially 0 0 state or something. How do I go to the next state, right? How do you say this inputs I would define in terms of, so that what I want I get that, right? That is what the main point would be. So that is called the state diagram. Means that whatever my initial state is, let's say qn, and from that I want to go qn plus 1, right? what inputs what input do I need to give, right? That is the simple questions I'm asking, that from this state, or I have to go from 1 to 0, what is that the input I need to give? So let's see some of the examples for doing that, and through which we can also figure out other kind of flip-flops which are existing, right? Not just this. So one other interesting is that this D flip-flop which we have already seen, when the input is 1, input is 0, you see that irrespective of what your qn is, your output is 0, right? That is what we have seen. So very, very direct. And when input is 1, irrespective of what your qn is, your output is 1, right? That is what the effectively we saw in the D flip-flop, right? And this is happening at the positive edge clock, right? If the clock is 0, we see when clock is 0, you see that the qn plus 1 will just retain the state, right? It retains the previous state, right? That is what we have seen as working. Now what we want is, and this is again going into the idea that now we want more than just that storage, right? We want some kind of state diagram. That means we are telling now that rather than you whatever you were, right, initially, I want you to be different. How do I want you to be different is, I say when your input is t, let's say, which is an external input I'm giving, whenever your input stage, whatever your input stage is, you just pass that input stage. So your when t, so simply writing, when t is 0, what I want is your qn plus 1 to be just qn, right? And when t is 1, what I want my qn plus 1 to be qn bar, right? Opposite of that. That is what I want. So that means with this condition, I can fill the, this would be 1 0, right? Like that. Now the question is, I want to build this kind of state table or this kind of system, right? Which is like a state table. This is a state table. You have already written what is the initial state you are in, what is the input, and what is the output you want. Now, but you have, let's say, available, what you have is a D flip flop, right? So you have D flip flop, which is available to you, Q and Q bar. And now which is available to you, I've given that. Now the question is, how do you, using this, can you make this kind of state table or this kind of state transition which we want, right? Can you make this toggle flip-flop, which is called toggle flip-flop, right? That is the code which we are looking at. So you see from the state diagram, one can try to do that. And what one can try to do that is that they know, okay, what if this was the case, the qn was becoming this, based on what should be my input should be if I want to do that. So that means now when we see D, we have to derive as a function of T, which is the input to the state diagram, right? These are these inputs, which is T, for example. This is the qn which you are getting here, right? and the next state, whatever the output comes, right, which is what we are defining as that this is what our qn should be. So this is a function of q and qn, which is what I have to make. So then when you see, if my t is 0, my qn is 0, and I want 0 as an output, right, what should be d? That is the question you are asking, right? What should be d? What? So then you know that when qn is 0 and you want qn1 as an output, what should be d? This is no change, right? So this could be 0, right? Because this is similar to, we are only going to look at this table, these two columns which we have, and we are just going to reverse from this, right? That is what we are going to do. 0 0, okay, 0, very nice. 1 1 1, right? Simply 0 1, when we see 0 1 here, right? So we are going to see with this table, right? That is what we are relating these two tables, and then so we are writing d. So when we see 0 1 0 1, here is 0 1 is 1, right? And then we see what is 1 0 1 0 is 0, right? So that is how we have written. So that means now you have got d table, what it should be. If you want this kind of state transition, you want this kind of qn and qn1 plus relation, right? So for that, you see now you have inputs and you have output. Qn plus 1 is obviously your output, but we want to write that in terms of d, right? Because that is what the main thing is, that we are feeding that as a d. D is function of this two, right? That is how you will get the next state. So now we have figured out d. Now it's just the three things, right? So we can say that we can focus on just a simple table where you have t, you have qn, and you have d, right? That is all. And d is your output, right? So then you say 0 0 0 0 1 1 1 0 1, and then the next state, which is your 1 1 0, right? This is the table which one can build, and based on that, now you know how to describe d in terms of qn. You can make a simple Carnot map if you want to, or you can do just simply just looking at this itself. So you can see that your d, when this is a truth table of XOR gate. So basically t is nothing, it's an XOR combination of qn. So then if I want to make this t, then you can see clearly that I have to take qn, whatever my q is, and I have to take t, which is my input somewhere, t, and then I have to connect an XOR gate, right? So let's take t here, bottom, yeah, right. Uh, and this has to go to d, and this is coming from q. So then you know that now this is going to give you the same transition table, and which you can verify, right? So when my t is 1, I know that when t is 1, then only it's going to invert, right? When t is 0, then it's just going to pass in whatever qn is coming. So if qn was 0, which is coming, then you know that what you are going to get is next 0. If qn was 1, then you are going to get 1, right? Which is what the basically truth table of the toggle flip-flop was there. So that means with a simple state diagram or state table like this, right? This is a state table we are drawing, which you have seen that now you have able to design this circuit using some kind of, this is obviously your combination logic, right? And this is what is your storage element, right? Okay. So one problem before we go away, I will give before you can try on your own, but I can guide. So yeah, I mean, similar to your D flip flop, you have SR flip flop, which is very similar to what we see, right? So here you are, as you rightly guessed, you are going to get a ambiguous state, right? At 1 1. So this is the state which we have seen in the latches also, right? So here also you are going to get this same state, and this is positive edge clock. So this is probably, I think, made with the NOR latches, because in NOR latches only we saw this happening at 1 1, right? In the NAND it was happening at 0 0. So then if you know this, then the question is, how do you remove this, right? And one way we saw that we could convert this to uh, where we said, okay, we are going to now give my set to this kind of thing, or like say opposite to this, right? Because D is 1, then output should be 1, right? So yeah, this was what we already saw, right? So this is a simple example of one can make also D flip-flop using just this, right? If you have SR. So if you have SR flip-flop, you know that you can make a D flip-flop just with by connecting this. Because when you do that, you see that you are only going to deal with these two cases, right? So this is when D is 1, and this is when D is 0, right? Which is what you also get in the flip-flop, right? That this is what is happening. And when clock is 0, when you know that the clock, there is no clock, which is the retaining state of this happening, right? So now the question, one question which comes is that, okay, now if I want to make two input thing rather than losing one input condition, if I want to have all the four states, yeah, right? All the four states I want to have, what do I do? So that is the case we are going to discuss, which is what we say, okay, you have the SR flip-flop with you, which gives this truth table, which we have seen, right? But what I want is rather than this ambiguous, I just want an interesting output, which is my toggle, right? So that means when, and we just name this whole thing as the inputs as the J and K, right? J and K are the inputs, two inputs I'm giving. Based on this input, my state and the Qn and Qn plus one, sorry, Qn bar, my next state should be decided, right? That is what you are going to do. And next state is, now you know that your initial state what it should be, and your next state what you desire is obviously this, right? So that is why this would form a state diagram, because you see that these are the states which you are going to get from SR, right? But I want to go to, rather than this ambiguous state, I want to go to this state. That is what my desire is. And for that, what kind of inputs do I need? That all of that you have to do. So for that exercise, one methodology we have already discussed, making a excitation table or a state table, right, which we were making. So excitation table is what is the question is that obviously what is the next state which I want, right? So we have already seen that when Qn is 0, right? When Qn is 0 here, this is your Qn. What I want is there is 0, right? This is 0, 0. There is no change in the Qn which is happening, right? Then same way we see if the Qn is 0, but the input or the transition of the flip-flop output which is happening 0 to 1, right? So that means this is the reset condition, which is what you are having. So for the reset condition, sorry, what is that? No, yeah, sorry, input at the FF, transition at the FF input you are having, right? So excitation table, what it is telling you is that the present state what you are in, and the next state transition what you would have, right? So now you see, because we want to transition to when it is 0 to 0 is no change, right? This is the same condition we want. Okay, then we want, if the other condition is, which is a toggle condition, when J and K are both changing, then we want this to toggle, right? When J and K, we see that our what is happening to J and K is that this is 1, and this is again going to, let's say, reset, right? And this is going to set kind of thing. So that means you are already building this table where what you are trying to do is you are trying to look at for what inputs of SR would these condition be met, right? That is what you are trying to do. So a better way of doing this is in this form, which I just drew, right? This is just a SR table, which I think we all know, SR truth table, but written in a different way. But this is the main thing, which is what our state table is, right? Which is what we have been taught. So state table is, this is my Qn, right? This is my input because this is what I want. When Qn, so there are three inputs which I am having. One is the state Qn, which I am getting from the flip-flop. J and K are my external inputs, and based on that, I want to decide my next state. So when Q is there, J and K are 0. This is the no change state. So when this is there, this is 0, right? I know that there is no change in the input. When 0 and 1 are this one, where the input remains or the output remains 0, right? Qn remains 0. Qn plus 1 remains 0. So when 1 and 0 is there, then we know that this should become 1, right? Irrespective, I'm not even seeing Qn, right? Because that is what is the desired table. Then 1 1, now I see that it should toggle. So if it is 1 0 here, then this should become 1, right? Then same way 0 0, no change, right? So no change means this is going to give me 1. Then again I see 0 1, 0 1 means that it's 0. 1 0, no question asked. 1 1 toggle, so if it is 1, it becomes 0, right? So based on that, now you only focus on, this is where the excitation table becomes important, that you only focus on now these two, right? Because your inputs are anyway you have populated, and you see what is the different kind of outputs. So that means now SR, similar to what we did in the D flip flop, because we know now the circuit is going to look like something like this: SR flip flop, and then your clock. Give me 2 minutes. Then Q and Q bar are this, right? So Qn, and then this thing, the logic, which is what we were saying, there is some logic which is going to come for both Q and S and R, right? So the S and R out basically are this is combination logic. So we know that based on the previous state and the inputs of J and K, this is going to decide, right? This is what the state, yeah, this is what we saw. Based on S. So S and R are basically your output, right? In terms of J and K, you have to define. This is exactly the same thing which we did with the toggle flow, right? Where we defined based on the T, we defined how the D should be, right? Based on this state table. So that is exactly what you have to do. And then you have to use, so you use the same state table, you fill the state table for SNR. So you know one entry I can fill, that if I want my output to be 0, then the question is what are the two possibilities I have, right? So I know when this is happening, then the two possibilities are that either you are resetting, right? So that is one possibility, that it is resetting, or there's another possibility that this could be 0, right? Because it is retaining the state, the previous state. So that is why this thing has made as X. X means that either 1 or 0, this will remain at 0, right? So that is the X is coming from. Same way one can say, okay, when your Qn is turning to Qn plus 1. Now, what is that you need, right? So when this is becoming 1, that means either it is set as 1, right? Or you could say that it is toggling, right? But that condition is not there in SR flip flop. So it can only become 1 when the S and R are 1 and 0, right? Then only it can set the flip flop, which is what one can see as 1 0, right? So this is when 0 0, yeah. So this is 0 0 is again the same thing, 0x, and yeah, which is 1 1 0 1. This is what we saw, yeah, 0 1. So 0 1 ones which you see here, they will become 1 and 0, right? Then you have 1 and 1. 1 and 1 is again this one. Now this can become, because as we said, either set is there, it is a set condition, or it could be the no change condition, right? No change means 0, right? So then X, a set becomes X basically for 1 1. So set becomes X, for which is what we have written here also. So you can follow that. And 1 0, you can see now 1 0, there are two conditions, either 0 1, right? We are only focusing on these two, right? So 1 0 and 1 1, we already know 1 1 is X 0, right? And 1 0, you know that 1 0 is, what is 1 0? 1 0 is 0 1, right? So that is how you see that you have built now the table, and you know when the output is what, right? Based on the terms of now three inputs. So you will be focusing on these three inputs, and you have the output available, right? This thing. So when you have this available, then you can now figure out that, okay, what is happening in my S and R, right? So that means you're making table for S, one table for S, one table for R. And how many inputs you have? You have three inputs. One is Qn. So you have 8 entries, right? So this is R for R. Then you have 8 entries. So one entry is obviously your Qn and Qn bar, and one entry is your J and K, right? These are, and then you can, I'm fairly confident that you will be able to find the expression of S and R in terms of function of J, K, and Qn, right? That is what is the objective. So that once I get this, now I am able to decide that what state this should go into. But I'm making that using this circuit. And what you get is, when you do this thing, you will get simple these AND operation for the S and R using this, right? And then you can make this circuit where this circuit gives you this kind of truth table, which is also known as JK flip flop, right? So one, if one is defining JK flip flop, they can get that flip flop using this SR latch, which we have seen in the past, right? And then you can plan and just draw the waveform. You can practice that. And for JK flip flop, I think, yeah, that is all for this. And then there is another application one can look at, and then you can see if you give a toggle flip flop, what would be your Q when you have tied it to one, right? That is the condition which is given. So this is the condition when this is there, this is toggling, right? So you see that when you are registering the output, what is happening with this kind of thing, right? Yeah, this is what we have already seen. So I will upload these slides also, and I think you are all welcome to look at it, right? I mean, before our extra class tomorrow, if you are not planning on attending, then I think it's a good idea to look at it so that you can solve the tutorial questions and also look at the quiz. Okay, thank you. So with that, I would end here.